All right, everybody, welcome back. In this video, we start the second half of Unit 10 for AP Calculus BC. We're going to start with section 10.10, which is on the alternating series error bound. All right, so just a kind of a recap here, a lot of big text scrawl for you here. In the first half of the unit, we spent the vast majority discussing whether or not particular series would converge to a finite value or not. Something that we didn't really talk about was what those series would converge to. With the one big exception of geometric series, we had that formula to find the sum of those. One reason for this is that it's very difficult to actually find the exact numerical value that an infinite series converges to, or it can be difficult. Over the next couple of lessons, what we're going to do is we're going to learn some techniques and use some techniques that are going to allow us to do the next best thing. And that is determine an interval which has to contain the value to which the series converges. So we can kind of narrow it down without actually finding the value. And the way we're going to do that is we have some techniques to establish the maximum error that occurs when we're using a polynomial to approximate an infinite series. And we're going to start here with the alternating series error bound in this lesson and how it works. All right. In order to get us started, the first thing we're going to do is we are going to look at this infinite series, the sum from 1 to infinity of the quantity -1 to the n plus 1 all over n. We're going to find each term for the first 9 terms, and then we're going to graph the partial sum up to that term and see what it looks like. Okay, so first of all, when when n is 1, this is -1 to the second, so that's 1 over 1, so the value of that is 1. When n is 2, it's going to be -1 over 2, so this is going to be -1/2. And then the next term, the alternator makes it positive. It still looks like we're dealing with the alternating harmonic here. So we can fill in these values pretty easily. Along the way. And then I'm going to use my calculator to get the partial sums here, because I'm going to use decimal values of the partial sums, because after we have the partial sums, we're going to graph the partial sums on our coordinate grid that we have below. So let's go ahead and do that. We've got 1 minus 1/2 plus 1/3. So next partial sum is 0.83 repeating. And then we're going to subtract 1/4. That's 0.583. The 3 repeating. And then we're going to add 1/5. That's 0.783. The 3 repeating. Then we're going to subtract 1/6. And that's 0.616. The 6 repeating. And then we're going to add 1/7. It looks like this is where we run into, it looks like the digits start to repeat at this 9-5, 9-5-2-3-8, 9-5-2-4. It looks like those repeat there. Either way, I'm just going to go with the first. When I go to graph this, you're not going to be able to tell the difference between 0.7595 and 0.75952. Heck, I'm not going to be able to tell the difference between 0.75 and 0.759 when I go to graph this. And then we're going to subtract 1/8. And that gives us 0.6345. And then we're going to add 1/9. And that gives us 0.7456. Okay, so as we look at these values for this partial sum, you might notice that they bounce back and forth where, well, let me say that a little later on. All right, let's graph these partial sums. When n is 1, partial sum is 1. When n is 2, the partial sum is 0.5. Let's plot right there. Then 0.83, this is 0.85, so 0.83 is going to be right about here. 0.583, which is a little bit below 0.6. And then 0.783, which is a little bit below 0.8. And then 0.616. This is 0.65, so 0.616 is going to be right around here. 0.7595, so this is 0.75, so 0.7595 will be a little bit above that. 0.6345, right about there. And 0.7456. 0.7456, which is going to come in right around here. All right, so what you should notice as we're plotting these is these partial sums are homing in on the actual value of this series. Which, by the way, the actual value of this series is the natural log of 2, which is approximately 0.693. This is one where we do actually know the sum of this series. So there's the actual value. But what you see is that as we add terms, these hop back and forth over the actual value. So the first term and then the second term, and the third term added in, fourth term, fifth term, sixth term, so on. We're just bouncing back and forth over the actual value of the sum. And this illustrates to us what the error, I don't say anything else about it here, but on the next page we'll say it. This illustrates to us how I can bound the error. If I were to approximate this infinite series using just the first term, my error is smaller than the next term and in the same direction. So the approximation is below this partial sum, and it's smaller than the distance between this partial sum and the next partial sum. If I were to approximate this using the first two terms, the error is smaller than the next term, and it's in the same direction. The approximation is above, the next partial sum would be above, and the the actual value is closer to our approximation than our next partial sum would have been. This builds us to the alternating series error bound, which you're going to see in this box right here. If the series converges by the alternating series test, then the error from using the first n terms of the series to approximate the value of the series is less than or equal to the absolute value of the first omitted term. So the error, which is the difference between the sum and the nth partial sum, has to be less than or equal to the n plus first term, the absolute value of that. That's the error. Furthermore, the direction of the error will be the same as the first omitted term. Therefore, if the first omitted term is positive, then the actual value will be above the approximation. If the first omitted term is negative, then the actual value will be below the approximation. All right? That's it. That's the alternating series error bound. The error is always smaller than the next term, and the actual value is always in the same direction as that next term. So let's go ahead and in the rest of this video and maybe into a next video, we're going to do some alternating series error bound examples. Example 2. Determine the number of terms required to approximate the sum of the series, sum from 1 to infinity of -1 to the n over n, with an error less than 0.005. All right, so the absolute value of the n plus first term of this series, when I approximate it with n terms, is the absolute value of -1 to the n plus 1 over n plus 1. That's my error. My error has to be smaller than this. And we want the error to be less than 0.005. So we want this to be less than 0.005. The absolute value of this, the absolute value of this is going to be 1 over n plus 1. So in order for the error to be less than 0.005, we know the error is smaller than this, so we want that to be smaller than 0.005. And now we're going to go ahead and solve this for n, and that will give us the number of terms that are required to approximate the sum of the series with an error less than the required error. All right, so now it's just a matter of solving this equation for n. So I multiply both sides by n plus 1, and I divide both sides by 0.005. So we're going to do 1 divided by 0.005. That gives me 200. So 200 is less than n plus 1. Subtracting 1 from each side, that tells us that n has to be bigger than 199. The number of terms has to be bigger than 199. Therefore, the number of terms that we need is going to be 200. All right, example 3. If the series sum from 1 to infinity of -1 to the n times 1 over 3n minus 1 is approximated by the partial sum with 10 terms, what is the alternating series error bound? Okay, the error, since we're using 10 terms, the error is going to be less than the absolute value of the 11th term. So it's going to be less than -1 to the 11th over 3 times 11 minus 1. And so the error here has to be smaller than, and now I'm going to go ahead and calculate this. We want the absolute value, so I'm just going to leave out the -1 to the 11th power and just do the 1 over, looks like 32 when I do 3 times 11 minus 1. And so the error is less than 1 over 32, which is equivalent to 0.03125. And so the error, when I use 10 terms to approximate the series, has to be smaller than 0.03125. All right, that's where we're going to put an end to this video. We'll come back in the next one on this section and do a few more examples utilizing the alternating series error bound. Okay, until then, have a good one. See ya, everybody, and bye-bye now.